right, welcome everyone. We are now in week 3. Tonight we're going to look at the shortcuts for getting a derivative, help us understand kind of the derivative as a function. Now, some of the stuff we've been doing up to this point, like I said, we've taken out some of the sections like having to do factoring, having to do some of these other things, which is great. It got I think we jettisoned at least 2, probably 3 sections, but at the same time, you didn't really get the experience to work with derivatives that much yet. So you might be struggling with some of the sections. In fact, what we had 4 or 5 of you came to office hours. We were working through 10.3, 10.4, 10.5. So we'll keep working on those, but tonight we actually jump into chapter 11, and I think it will help build more understanding. But before we get into our content, we have a guest with us. You might notice when you go to Enter Canvas that there are actually 2 courses. There's our brief calculus, which I quickly go into, but there's also this SI course. What does SI stand for? Support. I'm not sure. So, but it's a yes. Say that again. Supplemental instruction. That makes sense now. Okay. Yes. So that's what it stands for. So it's some assistance we're getting specifically to 10. Every 210 class has this because we're all set up with the same homeworks and everything. So we have our SI student who will be working with us. So if you go into here, again, I'm not associated. This is my first time using that, so we'll kind of figure it out together, but it's supposed to be resources for all those things. Yes?
It says our test review is due tomorrow at 10:45.
Forget it. It's from last semester. I'll change the due date.
Okay.
It's not.
I was like, why is it due so far
Yeah.
before our test?
Because I forgot about.
No worries.
I didn't want to delete it yet. They got some new quizzes. I want to look at those and see which ones are actually going to be better. So don't take it. If you tried it anyway, yeah, just ignore it for now. Okay. Any questions? All good? Okay. So we'll go ahead and start in here. And okay. So I got a little bit ahead. I set up for Thursdays as well, which we'll get into our first application, marginal costs. How many of you have dealt with marginals before? It's a business thing that, right? So it's the price of the next thing. So when you're manufacturing, it's the price of the next. So that's actually a good use for the derivative, because the derivative is giving us what's the rate of change at a particular time. So we'll get to that, but for right now, what we're going to do is get into these shortcut methods, which is ways to find the derivative. So I pull up the slide deck from here. So I just also want to emphasize that you all have access to the slide decks. I'm trying to integrate more problems from the textbook that are similar to the ones in the homework. So I think we've got some in here, if I did it right. Yeah, we've got a few applications, and I even included one of the homeworks, but that'll be fine. Let's see. I think we can go ahead and get started. So techniques of finding the derivative. Let's see. Let me do something a little different. Hopefully I don't know where my window went. Let's see. let's do this. Let's see. I think I can just switch. There we go. Y'all see that all right? Kind of. Okay. So what I'm going to do, see if I can remember how to do this right. I'm going to look at a function. How about x squared? A simple function. What does x squared look like? Let's graph it. Let me do a zoom standard. So this is our from negative 10, so x squared, right? Nothing surprising. Parabola going up. In the homework, there's a few things. If we think about the derivative of this function, what is the derivative? It's another word we use for the derivative. It's a rate of change. Rate of change of what? A particular type of line. Not the secant line, the tangent line, right? So this is an instantaneous rate of change. So it's the rate of change at a given point. And so a tangent line just goes through the curve at one point, not 2 points, right? So we can think of the tangent line as kind of following the curve around. And so we see on this left side, it is decreasing, right? It's a line that would be going down. It looks like it's going to be about 0 here. We'll see it is. And then it increases on this side. So what would a function look like that was a derivative function? It was where the inputs are these same x values, but the output of the derivative function is the slope of all the various tangent lines. That was one of your homework problems. And you see that here, the derivative is negative, turning to positive. So if you chose the one that was a straight line going from negative to positive, you were correct, right? What I'm going to do is I'm going to show you how this calculator, it'll stay on, it has a couple different features, okay? Sometimes you'll get homework problems that will ask you to find the equation of the tangent line. So the tangent line has two things, right? It has a slope, the slope of the tangent line, that's what we call the derivative, but there's another part of every line, the slope and the y-intercept. Okay. So, and the y-intercept has nothing really to do so much to do with this, but we have to find it. But watch what happens. If I want to find the slope of the tangent line, let's say at -2, when x is -2, what I can do is there is a feature here, and it's on the program button. It's the draw. So draw is in blue, so I have to hit my blue button, and then I hit draw, and these are all the things I can draw. What do you think if I click on 5, what do you think it's going to draw? Tangent line, hopefully. That's what we're hoping, and that's what it does. So I'm going to go down to number 5. I'm going to draw a tangent line. Now, the thing is, you just say, okay, go ahead, draw it. Well, you have to tell it where you want, but the instructions don't tell you. So I have to put in -2, so I just start typing -2, and now it makes sense. It would make more sense if they put the x equals and have something waiting there, because otherwise you don't know what to do. So draw, tangent line, put in the value you want it, and watch what it'll do. It will actually draw the line, and then it actually gives you the equation of the tangent line. So we can see that the slope of the tangent line is -4. We see it's at x equals -2. And we see a y-intercept of -4, so that's going here, which sometimes we use these because we might use that tangent line to do a prediction. Okay, that's why we sometimes need that full equation. But what part of this is the derivative? Just the slope. So -4 is the derivative of the x squared function at -2. And we can do this, and I'll just leave that there. I'm going to go and draw another tangent line. This time I'm going to draw it at x equals 0, and you'll see it's horizontal. Is that kind of making sense? And then it gives me the new equation, slope of 0 plus 0. Okay. If I get the slope at positive 2, what do you think that's going to look like? Coming this way. What do you think the slope's going to be? Anybody? It was -4 for -2, so what do you think it's going to be for +2? All right. You wish you would have bet $1 million on it because it's 4. Okay, yes. So we get the symmetry. Okay. So we've got a function that when x was -2, the slope was -4. When x was 0, the slope was 0. When x was 2, the slope was +4. Okay. And so these are tangent lines, and so we're getting all these slopes of the tangent lines. So that's so far what we've been doing. But if I can remember how to do this right, I can actually have the calculator draw the function of the tangent, of the derivative. And I know I've done this before, but now I forgot how to do it, I think. Let's see, do I do it here? No, that's when I graph. Maybe it's here. I hit the math. The derivative. And derivative. And then the second part of the class we'll do integration. So remember sort of this part. What I'm going to have it do, though, is I'm going to have it take the derivative of that first function, and it's going to draw the graph. And remember, we're thinking that it should be negative and then positive. So let's go ahead and do that. So I'm going to do this. The derivative, and this kind of we'll talk about this in the lecture a little bit, but this is notation. So it's d dx. So we're telling it what we're taking the derivative with respect to. I don't know really what that means, but we're taking the derivative of x. Later in the course, we will actually take the derivative of y and x. It's called implicit derivative. So, but we start off, all we're doing is taking the derivative of just the x variable. Now, I could put x squared in there, but what I'm going to do is I'm going to show you that this calculator also has a function called vars for variables. And if I go to my y variables and I go to my functions, there's all my graphing functions. So I'm just going to put in y1. This is a nice way whenever we want to do something with that first function. So whatever I put in y1, it will now also always graph the derivative of y1. And then it could graph at a particular value. That's what this, if I want to say like x equals 6, it would just give me a constant. But I want x equals x. So this is going to give me the full function. And now when we graph this, out. Here it comes. This is actually the second one. So the red line is actually the derivative of x squared. What does it look like? Can anyone kind of guess at what this equation of this line is? It's not a tangent line. It's a graph of a derivative. Graph of the derivative of x squared. Can anyone kind of guess what that equation might be? Close?
Yes.
What's that?
2x.
2x. Y-intercept is 0, so 2x plus 0 if you want, but yeah, the 0's gone. So 2x. Now, and let me, let's see if I go to draw. I just want to, let's see. Go like that, turn it off. So what I want to do, that's the derivative, and what the way the calculator gets at is it actually went and it took the derivative at each point of x squared. So it numerically calculated it. Let's come back here, y3, which is going to be in green. Let's put in 2x to see if it is, because if it is 2x, what's going to happen? That red line's going to become green, because the green line will be right on top of it. And yeah, the red line just turned to a green line. So it's the function 2x. How could we get from x squared to 2x? because that's the shortcut we're going to use. Let's come back online. Let's go back to here. And I'll get my online, I don't know what happened. I did something today, I lost my screen, and now I can't get it back, and something I did weird. So let's get in here. What I'm going to do is, before this is kind of formally introducing it, but we had a function. Let's go back here. So f of x equals x squared. We looked at, just graphically, when we take the derivative of each point individually, we got a graph of 2x. And would you believe me if I said that all we have to do to get that is take the exponent, multiply it by the coefficient, and incidentally, what's the coefficient to x squared? 1. So there's really an invisible 1 there. So 1 times 2 gives us 2. And then how come there's no exponent now? It's 1. There actually is an exponent there. It's 1. How do we go from 2 to 1? Remember, I told you, if you know how to subtract 1 and multiply, you can take a derivative. That's all there is for pretty much everything we're going to do today. You take that exponent, first thing you do is you bring it down in front and multiply, and then you subtract 1 from it, and you'll have your derivative. That's kind of why we skipped a lot of the other stuff that was algebraically getting you there. It would give you some feeling, but I'll tell you, it's painful. I've been through it. And you don't know what you're doing until then we finally get to this. You go, oh. And hopefully we'll see that we didn't really have to do it. So help me with this one. What if my function, well, why don't we go with g of x? We'll use a different function name. What if it was 3x to the 5th? What's the derivative? 15, 3 times 5, right? So we'll change colors here. Again, the process is take the exponent, bring it down and multiply. So we're going to get 15, and then subtract 1 from the exponent, 15x to the 4th. You are now experts at taking derivatives. Okay. This whole lesson, that's basically what we're going to do. We're going to look at several other things, like what if you have more than just x to the 5th? What if there's more terms? We'll see. We do it term by term. We're going to be okay with that. It works. I've deleted all the proofs, because actually the PowerPoint had like 4 pages of proof on something, and I say my proof was the beginning. We did the graph, we had the calculator find the derivative, and we graphed the derivative, and they were the same. So we can accept. I mean, that's what business people do. If it is, it is, right? If it works, especially if you're in business law, right? This is legal because they say it's legal. If they change the law, then it's not legal, right? It's what they say it is. It is because it is. And that's really a lot of what math is. It's people have invented something, a way of seeing it. I was talking to some earlier that a lot of times in math, we could do it this way or we could do it that way. I want to do it this way, but they somehow decided to do it this way. And so I'm always doing things backwards or something, But it's not that what I'm doing is wrong, it's just that it doesn't fit with the officials of math who said, we will do it this way. But it would work this way if everything else was consistent. So it's kind of like for consistency, we move forward. Okay, so that's where we're going. That's where we've sort of been. So these are our shortcut rules. Again, they're going to more formalize it. Calculation of a derivative as a limit is often tedious. We did a little bit. We did a little bit with limits. And how many of you were just loving limits? Limits was a technique that allows us to say as we get close to something it exists. And all the reason we need limits for is that we let the distance between 2 points go down to 0 so we can get the slope at a point. Okay? So we can get the slope of the tangent line. That's all we really need the limit for. We don't use it much after this. because it's really just to say, hey, we can let these 2 points become 1 point. Now we've got instantaneous rate of change, we've got the derivative, and we've got some shortcut rules that will get us there. So it's just saying we could be using limits, but it's very tedious, a lot of algebraic stuff that goes on. So we're going to go right to the quicker method, which we just did. Right? So that's all it's saying. First one, good name for it's the power rule, because we're taking that power, multiplying, and then subtracting 1 from it. So just like we did, x squared, they start off, well, that's 2x. The 2 comes down in front, 2 times 1 is 2. Subtract 1 from the exponents, 2x to the 1. X to the 3 times 1 is 3. Subtract 1 from 3 and you get 2. So that's how they've started. This is it, right? And they just generalize it. If your function is just x to the n power, n is just any number, then bring that n down in front, multiply by 1, subtract 1 from the exponent. So it's just kind of a formula. So we can do this whatever it is. And we're going to see it doesn't have to be an integer either. It doesn't even have to be positive integer. It can be a negative exponent. So we'll start doing it. But the rule's the same whatever it is. Okay, and we'll go through several examples. And then like this. So, wow, how do I do this one? So, this first one, what's a way to write 1 over x? X to the negative 1, right. So it's really 1 over x to the 1. When it's in the denominator, I've heard it one book call it the elevator rule. So you move it up, and it would become negative. So what we want to do is do some algebra first. We'll say a is f of x equals x to the minus 1 power. That's exactly this. So 1 over x is exactly the same thing as x to the minus 1. We good with that? That's an algebra thing. Okay. If that's not clicking with you right yet, we'll go back, we'll look at some algebra. But it's also one of those things that it is because it is. It's sort of almost a definition. So, but knowing this, how do we take its derivative? What do we do with the exponent? Move it in front. Negative 1 times 1 is negative 1. And then what do? We subtract the 1. So this is where it's sometimes, subtract 1, it becomes negative 2. See, I blow things. So, yes. So this is the derivative of f of x. Same rule, it's just different. Now you can just, if you go directly from 1 over x, I'll say that's a negative, so there's going to be a negative in front, and then it's going to be x to the negative 2. You could then also rewrite this, right, as negative 1 over x squared. So you'll just be able to use both of them. Sometimes the question will ask for the answer with a positive exponent, so we got to go to this. Again, this is an algebra step, it's not a calculus step, but this is still a right answer, but multiple ways of writing things. Okay, but I think it's, especially in the beginning, it's good to rewrite them with exponents, so you can see, okay, just take it down. If you try to do too much in your head, take it from experience, that's where I make my mistakes, and because I forget a negative, or when I subtract 1, I go the wrong way or something. Might end up with 0, right? Okay, so same thing with this one, with the B question, right? So how do we write 1 over x squared? X to the minus 2. And again, nothing big deal, just bring that exponent down and subtract 1 from the exponent. So it's going to give us a negative 2, x to the negative 3. And that's what we call the derivative function. Now, if we want to find the derivative at a specific point, we can actually just plug it in here, get the numerical value. Okay, so we're getting some really good power here. But it also allows us to graph this, which is the function graph, and then graph this, which is the derivative graph, and we'll see how things are changing. Remember, this graph with this little prime, it's a whole different, this output is a different, this is not a, it's not a y value so much. I mean, it is, but it isn't, right? It is a rate of change. These outputs are all how things are changing. And so it's a rate of change at that point. Up here, this is a function value. So this is like a profit graph. This is actual how much profit you make. This would be how the profit's changing. Right? It's not how much profit you're making, it's how the profit changes. Profit, profit changing. Cost, cost changing. Whatever. So the derivative is always how it's changing. The original function gives us the value. And that's one of those things you're going to want to keep reminding yourself, because it's so easy to confuse. I'll confuse myself even after all of these years of teaching it, because you're going back and forth, and I get dizzy real quick. Okay, so we'll look at this one. C. How do we write a square root function as an exponent? 1/2, 1/2, 0.5, however you want to do it. It's a half power. So a root is a half power. A cube root would be a third power. A fourth root is a fourth power. So we'll start using those. Again, this comes from algebra, but and again, we could do it either 1/2 or we could do it as 0.5. But you'll see that what typically starts happening now is now we've got fractions, and I've got to be able to add and subtract fractions. And that's still a pain. I mean, even if you can do it, it's a little bit of a pain, right? So what I'm going to propose here is, as we do this, we can go ahead and say, okay, yeah, bring this down. So that's going to be 1/2 x. But when I subtract, I'm not going to subtract 1. Well, I am going to subtract 1, but I'm going to subtract it with a common denominator. So what is 1 with a common denominator of 2? 2/2. And if it was 1/3, I would have subtracted 3/3. Just go there, because that's going to get you your common denominator. And so I get 1 minus 2. I end up with a negative 1/2 power. Okay, so that's my derivative function. And again, this is where it gets a little strange, but this is the algebra part. We're going to write this with a positive exponent. What happens to this x to the minus 1/2? It drops down into the basement. And we could see that we could write this as 1. The 2's already in the basement, so we leave that there. And then x to the 1/2 down here, I could also write that as square root of x. So you'll see that. You could also write it as x to the 1/2, a positive 1/2 down there, but this is, again, sometimes the hardest part of the calculus is all the algebra that goes behind it. Again, the calculus step is bring down the exponent, subtract 1 from it. Not too bad. What ends up happening in the homework, too, as we get more complicated, is then getting it in the right format for what it's asking for sometimes. But show your work. You know, on the exams, I do collect your scratch paper. So if you can, when you work something out, if you show something and you had this and you like made a mistake down here, I can give some partial credit. So we'll get you there, even on a multiple choice. But get in the habit of writing down your steps, especially as you go, because it'll help you. And then if you do make mistakes, you'll know what it is. Because otherwise, if you do it all mentally, which is a great way to do it once you get going, when you make the mistake, you think you did everything right. At least I do. I don't make mistakes, do I? And yet there was a mistake that was made somewhere along the line, and then you basically have to rework it all. And so just write down kind of the steps you do as you do them. Kind of get in that habit. It's not that I don't have a policy. If you don't show your work, no points. That kind of. It's not. Don't show your work for me. Show your work for you, so that when you come back tomorrow, you know what you did. And if you come back tomorrow and you didn't show much work, but you can look at it and you know what you did, then you've arrived, right? So that's the thing, is show enough work that you know what you're doing. And again, I always I wake up the next day, how did I do all this stuff? I I should have wrote down some notes, right? Because I didn't remember. So that's how we go. So far, so good? So again, simple power rule. What we're going to see as we move forward, there is, we'll just get into notation differences, which is not a big deal. But as we go forward, there's going to be some other rules, like if we're multiplying two functions, we're going to have something that it gets a little tricky, but we'll get there. Okay, those are actually, I think they're into the next test because we've got 2 more sections. One section is going to be just doing some simple derivatives with this, so some practice with it, and then we'll get some more. Okay, so again, this is kind of wordy. What I'm going to tell you is that there are 2 different ways for writing the derivative. So if you want to read through it, you can read through it. I'll give you the Reader's Digest version. So we can say f of x prime, or f prime of x, right? This is the derivative. Of f of x. The other notation is d dx, which is read sort of, the d is derivative with respect to x of a function. And this one, usually what they do, we could put f of x here, but usually they would do something like this. So d dx of x squared is then going to be equal to 2x, right? So it's a different notation. And the reason there are 2 different notations, there are 2 people who are credited with discovering calculus. Again, credited. I'm sure there's people that lived way before them that found it too. But one guy was named, some British guy. Anyone know, had an apple fall on his head? Newton, yeah. So Newton. And Newton came up with this. This is one I like, maybe because my dad's British. This suits me better. So I like this one. The German guy, I forgot his name, Leibniz. Or is it Leibniz, yeah. Or is he French?
No.
We'll call him European. I can't remember if it's German or French, but he wasn't English. He discovered his calculus at about the same time, and they have sort of similar rules, but he had a different notation. And this is sort of how they said, you both discovered the same thing, but they didn't work together on it, and they had different notations. So down to this day, we'll use different notation. Okay. Sometimes this is helpful because this gives us some tricks of being able to sort of use fractions. Okay. We'll also use this notation because a lot of times the function is, we start off with like y equals x squared, and so we might call this dy dx, so the derivative of y with respect to x. So you'll just see these, and I tell you what, when I first time through, I just sort of ignored the differences. I didn't like this fraction stuff, so I would just convert it to the f prime. But we'll use this technique a little bit later. And there's a couple questions in there where they'll use it, so just kind of know that it's there, but don't get too stressed out about it. Is that okay? Okay, and again, you can kind of go through here. Yeah, d dx of x is that we're getting, it's the same thing as this. And so for me, I'm just going to stick with one notation for now until I get comfortable doing it, and then we'll use this down the road. And it does have some advantages later down the road. So d dx is just the derivative with respect to x, or if we've got another variable, dy dx. Or maybe we're doing circles, and so we've got volume, dv, dr. So sometimes it's helpful, okay, when we've got multiple variables going on. But we're going to stick pretty much with the function notation for this first part, with the exception of a couple homework problems have this notation in there. Okay, so again, we don't worry too much about it. We know how to do it. It just says take the derivative of x to the third, take the exponent down, subtract 1 from it. That's what it is. Okay. And here's our first rule. So we have the power rule if we only have one term, x to the 5th, right? Bring the 5 down, that's 5x to the 4th. What if we have multiple things that are being added and subtracted? So what if our function looked like x to the 5th plus 3x squared minus 4x. What do you think we need to do? What's that?
Do all of them individually?
Good. You're kind of what you okay. So this one, I threw this one in. I was going to put a constant, but we've got a rule for that, so we'll see that works. But this one, in a sense, the x will go away. But let's go ahead. What the rule ends up, whether we're adding or subtracting, yes, do it piece by piece. And again, that's where they had about 3 pages of proof to show that if you take the derivatives of each one and add them together, you get the same thing as if you were to take the whole derivative. But again, it was kind of overkill. So yes, to take this derivative, simply what we're going to do is just in each case, the 5 comes down, subtract 1, it's going to be x to the 4th. 2 comes down, 2 times 3 is 6. We're going to subtract 1, so that's 1. What's the exponent here? It's 1, so 1 times negative 4, negative 4. Subtract 1 from 1, and what do we get? X to the 0. What's x to the 0? It's 1. So that's why. So then the x will disappear from there. But there still is negative 4, so we get 5x to the 4th plus 6x to the 1 minus 4. Now I'm going to, yes?
Oh, great. So if you had just left it as for the top equation as 4 and not put the x, you just leave that one and find the derivative of the other one, of the other two, and then you just bring the 4 down.
That could be.
I was going to ask, what do you do if 4 was just
Okay, let's think, what is 4? Because I was trying to avoid this, but I figured you'd want to go there. So 4, if by a function by itself, it would be y equals 4. What does the graph of y equals 4 look like? It's a horizontal line at 4, right? That's the graph. What's the slope of that horizontal line? So when you take its derivative, it's going to be 0. Okay, so that's whenever we have a constant, something without a variable, we still take its derivative, but what we're going to see is when we take this derivative, and I'll just put the prime here, or ddx, when we take the derivative of a constant, it's 0. So it's plus 0. We just drop it off because we don't need a plus 0. Plus 0 is nothing, right? So that's the one that disappears. I mean, it's completely gone. The other one is when it's just x to the 1 power, the variable part will disappear and it becomes a constant. Okay, and those actually are sometimes the hardest part. I mean, it seems simple, but it's not. This is where a lot, I made this mistake a lot of times. Forget this part. Or you forget, or you just bring the 4 down, and then maybe combine them or something, but no. Anytime there's a constant, its derivative is going to be 0. We'll see in a couple slides. There's actually a rule that says that. But otherwise, we're going, this is really nice rule. We just take it term by term. It's not so easy when we get to dividing and multiplying. We've got to do some special things. Just like, think about FOIL, right? If you multiply 2 binomials, you can't just multiply the first ones. There's a whole sort of formula. That's kind of what's going to happen when we get to the derivative when we multiply, but we won't get there till a while. All right. So the sum rule, again, the hardest part of this is the way it's written. So this says if we've got, what does it say? Oh, if we've got 2 functions that are being added together or subtracted, okay, and that's the case on the last one. I guess we could look at each of those terms as a separate function, right? Then the derivative of the combination of them is the derivative of each piece by itself. That's basically what that says. Then, and also if we were multiplying a function by a constant, then that constant times the derivative. Okay, and this last one, this constant multiple rule, we've kind of already been doing that. That's if we had, notice if I had x to the fifth, that becomes 5x to the fourth. And if I had 4x to the fifth, when I take that derivative, that becomes 20x to the fourth. So it's just saying that, yeah, if there's a constant in front of the function, we multiply. And we kind of just sort of naturally did that. Makes sense, and it works. Okay. Sum rule, sum and difference rule, just term by term take their derivatives. We're good. Okay. I guess they didn't have much to say. They say the same thing, but with a new notation. So again, you sort of just get used to this. But again, for me, the first time I went through derivatives, having two different ways of writing it was confusing. So I just focus on the primes. But okay, we could use this. It's just a different, one was the British, one was the Germans or the French. Yeah. Here's an example. Again, we've got two functions being subtracted is what we look at this. So we take the derivative of each one. We've got sort of a constant multiplier here, so this negative 1 carries through. But it's just 2x to the first, 4x to the third. So we get that, and they're still being subtracted. So again, they throw back and forth the notation. We also could have written this as f of x equals x squared minus x to the fourth, and then just, I like to do it like this way because then I just write it right underneath, and it just tends to make more sense. 2x to the 1 minus 4x to the third. Incidentally, since this part of the class we are multiplying and then subtracting by 1, what do you think is the second half of the class? Dividing and adding 1. Exactly. Because we're going to learn how to integrate, which is just the opposite of a derivative. We'll also get to see what it means, but so the key parts of calculus are subtracting 1, multiplying and subtracting 1, which we can do. Again, and then organizing it. And then the second part is going to be basically starting with this and going back to this. We start with the derivative, get back to the original function. That's the second part of the course. Okay. So, and I only bring that up because as you take these derivatives, kind of reflect on them and get these set in your mind as a pair. Because when I give you this later on, you'll remember, you're more likely to remember the pair when we need to go backwards. Okay. It's kind of, and especially when we do some of these trickier rules and stuff. But each time, say I start with this is the end result. And the more you get that ingrained as part of your thinking, the easier the second half of the course will be. In fact, it'll almost be, yeah, I can look at it. It's just like, how many of you learned division by just doing the reverse of multiplication? And I literally would take that multiplication table, I'd look it up backwards. That's how I did it. And that's basically what we're going to be doing. So, good. Find the derivatives. Okay, so I shortened it. Again, this just examples. 2 times 3 gives us 6. Subtract 1, x to the 1. Here's a 1. 1 times 2 is 2. Subtract the 1, we got x to the 0, which is 1. Be careful, sometimes you think, oh, that's 0. No, it's 1. So it's just the 2. And then the derivative of a constant, 0. Doesn't matter what's being added or subtracted, 0 is 0. Right? You can subtract 0 or add 0, it's gone. That's it. This is our answer. I'll get rid of that. Okay? And again, important thing to remember whenever we get a derivative, what is a derivative? It's a rate of change. What's another word? The tangent, what part of the tangent? Slope of the tangent line at the point, and an instantaneous rate of change, right? So all those things, it's a slope at a point, at a single point. So always keep, and it's just going to make, as we get into the applications, everything so much smoother. Okay, now we're getting into the more advanced. But nothing too bad, right? So what's this first part? It's really just 2/3 x to the first, so the fraction's just going to go along. How about this 6 over x? How do we want to rewrite that one? -1. And then this one, we've got two, again, we've got the 2/3 is really just a fraction. It's a constant. And x to the 0.2, since it's in the denominator, if we bring it upstairs, it's going to become negative 0.2. And then we've got, I'm just going to rewrite this half as 1/2 x to the 4th. So just kind of, we've got fractions, just bring them in front, they're a constant, right? So it's just a multiplier. We okay with that step?
1 second, just so.
Oh, sure. Yeah, slow down a bit. Yeah, I need some water. Okay. Now, actually, yes, sir. This one? It's up in the numerator, so it's a +4. So it's really just that. All I did is say that, oh, it's over 2. I can rewrite that as multiplied by 1/2. So dividing by 2 is the same thing as 1/2. But that's, and again, if you want, you could leave them all as fractions and put these up in the top. It's kind of work in the way that makes sense to you. Question?
So why x 0.2 begin to minus 0.2?
Because it was in the denominator, I'm going to move it up. So that it's actually, because when I take that derivative, when I subtract one, I'm going to get a larger number. I'm going to get more negative, right? Negative 0.2, I'm going to get negative 1.2. If I don't do that, in my mind, I'll tell you, I will write 0.8. Because I'll see 0.2 minus 1, that's 0.8. But I would be wrong because anything in the denominator is actually a negative exponent. So I'm getting everything sort of up to the line that I can deal with it. If there were any square roots, I write those as fractional exponents, and then we subtract from there. So this actually is a fractional exponent, but it's written as a decimal. Okay. Yes.
What does the triangle mean?
Oh, that's my pen. Sorry. Yeah. Okay. So what I'm going to do is I'm going to take 45-second break. Let's give you a head start. See how far you can get, and then we'll do it together. So let's see if you can get it. Get the derivative. So this is the function. All I did is did the algebra to rewrite it. So go ahead and take its derivative. Remember, bring the exponent down, multiply, subtract 1. If you can do it mentally, great. Write it down. But it's always actually, it's a good thing to make a mistake in the early stages, because then you'll catch it and then you'll remember it. You actually learn more when you make mistakes than if you get it all right the first time. Trust me. I make lots of mistakes, and that's why I learn. Okay. That was 45 seconds, believe it or not. So this first part, what's 1 times 2/3? 2/3. What's 1 minus 1? 0. X to the 0 is 1, so that's all that's left there. And so that's one term. And then we've got this minus. I'll go ahead and put that. So we've got a negative exponent, right? Negative 1 times negative 6, so that's going to make it a +6. Subtract 1 from the exponent. Sometimes I like to write it up there, so that's x to the -2. Again, that's one where I could have some problems with, because maybe I think that's 0, but yeah. So that's, take the ones from the denominator, move them up, use the negative exponents. Okay, then we've got 2/3 times negative. There you go. negative 0.2 times 2/3. What I'm going to do, I'm just going to bring it down and put it off, because if I try to do it in my head, you know, but I'm just going to show that's all I do is bring it down and I'm going to multiply it. Yes? 2 over what? Oh, okay. So you could, that, yeah, you're ahead of me. I was going to just take the 0.2 times 0.2 and get 0.4 over 3, and then you got to convert that. But so, okay. But before we go further, we'll come back here. We also have to subtract 1 from the exponent, right? So negative 2 minus 1. Remember, when you're taking negatives, you add them together. So that's negative 1.2. And there's a couple ways. So you might recognize that 0.2 is 1/5, and then you could just go that route. I'm not that bright. So I just take 2 times 0.2, so I get negative 0.4 over 3. But the system kind of likes to have, I mean, you could divide by 3, but you're going to get a repeating decimal, right? And the system doesn't really like them. So I like your way of saying, the other way is thinking that we've got 2/3 times negative 1/5. So yeah, that's going to be negative 2/15, right? Okay. X to the negative 1.5.
If you put the decimal for that too, would it count as wrong, or?
Try it. If it's a fill in the blank, you'll get multiple choice. Then I don't always know. When you do use decimals, though, try to use as many decimal places as you can. So if you get a 0.333, maybe use 5 decimal places, and it's more likely to get there. Because most of the time, it's actually doing a calculation as well. But sometimes it'll say, no, I want the fraction, or doesn't understand. And I'm not sure what this, it's been a while since I've done this system. Okay, so we're good so far. And then the last one, right? This 4 comes down, so 1/2 times 4. 4 divided by 2 is 2. I'll just drop it down. So it's actually still negative, right? Negative 2x to the 3rd, right? Subtract 1. So that's our derivative. How'd you do? You know, and again, you'll find the areas where, yeah, this one's kind of I would work a little bit on this myself. Some of you just see it, you know it. So you find the areas where you struggle a bit. Fractions are still a problem for me, but I can get through them. But what I typically will do is I will write the steps down, because I don't want to deal with this, because this, if I start dealing with it, I'll probably get the rest of it wrong. Yes. Oh, I made a mistake. Thanks. Good. You got it. Oh, that's a special rule. So yeah, this still should be 1.2. So that's the other problem, is watch yourself. I know that sometimes you don't want to write more steps, because every time you make a step, you have the possibility of making a copy error. And those are sort of my favorite errors to make. I make them all the time. So yes, it should still be 1.2. Negative 1.2. Thanks for catching that. Good. We okay? Okay, so again, simple rule, take it down, multiply. But you can see there's going to be, we've got fractions in here, it just gets a little tedious as we go through. Just a couple more rules. So here's a constant multiplier. So yeah, if we have just some number times x and we take its derivative, it's just that number. So we did that 4x, the derivative was 4. If it is just a number with no variable, that's a horizontal line, so its slope is 0. So again, here's just putting it out there, and there's some quick examples. Okay, so we kind of, it sort of made sense when we did it, right? Okay, so it's there. So now let's look at a couple. These are getting, this actually is from the homework copy of the screen. What you'll see is you'll have this, but you might have different numbers here. So I thought we'd just go through it, one of the applications, and see how we do. So if a stone is thrown down at 104 feet per second, and what's 104 feet per second? What kind of a number is that? It's a rate, right? It's a rate. So that's actually a derivative. So from a height of 1,200 feet, its height s seconds after t, or height s after t seconds is given by this function. Now, this is a rate, but there's also, anyone know what this is? Any physics people? It's a negative force that's all around the Earth called gravity. Yeah. So this, and you'll see it, it's 16 feet per second. So this is the, in measuring feet. If you measure it in meters, I think you'll see negative 32 meters per second. But anyway, it's a constant. So you'll see this negative 16 t squared. That's the force of gravity. This is the force of the rock being thrown down, the initial rate of change. And this is where it started, right? It started at 1,200 feet, and they flew down. But what we want to find is, so what do you think is when I throw that rock down, is it going to get faster or is it going to get slower? Probably faster, because now the speed we're going to get is going to be a velocity. It's actually going to be more negative, which is faster, but it's because it's going down. The negative indicates downward force instead of upward force. Okay. If we threw it up in the air at this, then it would go up, but the gravity always wins and would bring it back down. Okay, so that's kind of what's going on. So let's compute the derivative together. So what's the derivative of 1,200? 0. It's a number, no variable. So that's the nice part. We get rid of all the big numbers. So 0. I'm going to write it in here just so it's taking up space. Negative 104t. So that's to the 1. So it is negative 104. The variable is t to the 0 now, so it's gone. So it's just negative 104. And then how about the last part? 2 times 16 is 32. 2 minus 1 is 1. So we get this. This is our function now. Negative 104 minus 32t. So what is that? That is going to give us the rate of change. So this is really the speed. So you can see as the time goes on, it becomes more negative. So you were right, it's going to pick up speed, right? Gravity's pulling it down. Started at this, we're going to basically get more negative in speed. So faster, but still heading down. Homework wants us to say, okay, now that we've got this function, we can easily find the derivative at any point we want, because we use, I get sloppy here, we use the derivative function. So s of 0, we put in 0 for t, right? So s of 0, if we put in 0 for t, what do we have? If we put in 1, so yeah, negative 136 arithmetic. 2, again, you could, yeah. Mostly I just wanted you to see how to do it so you get the derivative, and then we're just plugging it in. Oh, my calculator's not working. The other thing I would do, that's what I was supposed to do. Is, because I want to encourage you to be using these as a tool, because what it helps you to do is when you get in the arithmetic part and you're plugging in numbers and stuff, oftentimes what you do is you at least what I do, it takes me away from the problem solving. I forget what I'm getting. If I do it this way, I come in here, I'll just clear all this other stuff out. Clear, clear, clear. So if I put that in here, so it's negative 104 minus 32x instead of t. So I put in the derivative function. I can then just go over to my table. Let me go to table set. I'm going to have it start at 0. I'm going to have it change by 1, and I'm going to put it on auto so that I go second table, and now I've got all my answers right here. And you see, now I'm focusing on this rock falling, and I can see it getting faster. My mind has not been put on a tangent, if you will, doing the calculations. And you see me, I make calculation errors, and then it's also using a different part of the brain. And now I can focus on, oh, the rock's getting faster, and I can just copy these things down. Okay. Also, there's going to be one more question. We can use this to answer the graphing calculator to answer the question. Instead of going back and forth, the second question is, how fast is the rock going when it hits the ground? Now, we've got the function. We know, like at 5 seconds it was negative 32, but will this tell us when it hit the ground? Just getting fast. Now, when it hits the ground, it's going to stop, right? Unless it's a big rock, it might put a crater, but it's going to stop. But the math doesn't know that. How can we find when the rock hits the ground? We go back to the original function, and we find when because that original function tells us the height of the rock, we find out how long before that height becomes 0. Okay, and that's, again, the reason I want to go here is I've got to keep track of 2 different functions. The position function, I want to find when that's 0. When I find that value, I want to be able to plug it into the derivative function to figure out how fast it was going. So what I need to do is go back here. I'll just put it in y2. And what was it? It was 12, oh, it's right here. 1200 minus 104x minus 16x squared. Okay. And a lot of these problems, we're going to need to use both. The original function to get some kind of value, and then we're also going to need that derivative value, which is telling us how it's changing. And in this case, it'll tell us the speed. So what I'm going to do, I'm going to go up here. I'm going to turn this one off by just hitting enter. Notice that the equal sign is now light, so it's not going to graph it. Because I just want to focus on this. 1200, it's where it's starting. That's a y value, right? So at time 0, if you put in 0 for x's, it's at 1200. So just to help out a little bit, I'm going to set up my window with a y max of 1300, just a little bit bigger. I know I'll be at 1200, and then it's coming down. X is going up to 10 from my table. I think it'll be hitting within 10 seconds. If not, you can make that bigger. But let's go ahead and look at the graph. Goes up. Oh, okay. So I was expecting it to be up there, but that's okay. So at 1200 is where I start. I'm on some cliff. I throw it down. That's where it crosses the x-axis. That's where it hits the ground. I just need to find that. Looks like it's 5. I think it's 5, but I can also find the exact value by going second calc, using the tool to find the 0. That's where it will cross the x-axis. It's when it's got 0 height. To do that, take my little cursor, and it's looking for a left bound, so I'm going to take it down, and I'm going to just hit enter here because this is to the left of the x-intercept. Hit enter. And then I go down and to the right, I hit enter for a guess, and then it comes back. Oh, that was at 5. Maybe it changed on me. I don't know. Anyway, it's telling me it's at 6 seconds, right? So now what do I do with that? So I know it hit the ground after 6 seconds, but the question is, how fast was it going? Where do I find that? Go back to the derivative. So again, I like to do this, turn off the function so I don't get confused by that. Turn on the derivative function, plug in 6, or in this case, go to the table. going 296 miles per hour, or feet per second, I think is what it is. You get your units. The negative means it was going down. Okay.
Here's what I found.
Shh. Okay. I realize though, sorry for those who are watching the, if you watch the video, you'll hear everything, but you won't see what I was doing with the calculator. I'll maybe try to go back and fill that in, but we'll see. Okay. That's why I got to get my calculator fixed here. So we can put all those in. I'll just hit enter. This last one, when does a stone reach the ground and how fast is it traveling? The stone is traveling at a velocity of, now velocity includes direction, right? Speed itself doesn't include direction. So we could say just 296 miles per hour. But when they ask for velocity, we do need that negative to indicate direction, because velocity includes both the speed and the direction. So that should be there. Feet per second when it hits the ground at 6 seconds. Okay. The reason I wanted to do this one together, give you that feel for, we're going to have two functions. We have an original function that gives us values, in this case height, and then we've got our derivative function, which gives us, in this case, velocity, speed. Okay, and as we work with everything, Thursday we're going to do profit, loss, and costs. So profit is a function value. The rate the profit's changing is going to be the derivative. Let me see if I got, oh, I have a blank sheet in case I needed more room. So that's the end of the lecture. Is it feeling good? Okay, so if you need anything, let me know. If you need an extension, let me know. I have no problems with doing that. It's always best if you can just email me. I'll have your name and have a good one.
Hello. I want to ask, do we need to do this, the reputational quiz?
No, I'm gonna take that out. That's too early. We will have one, but that's next week when we get to the review for the test. That's the only time we'll have quizzes, but my bad, I forgot to take it out. Okay, thanks.
So I'm not gonna need that.
Okay. Usually by the morning, Friday morning. Yeah.
Thank you.
I have class after this till like 10. Ready to finish so I can ready.
Sure, but send me an email. Otherwise I'll forget.
It's yeah, it's just on 10.4.
Okay. I'm going back to my office, so if I remember, but if you could send me. Yeah, just send me an, yeah, no worries.
Thank you so much.
You're welcome.
I had a question.
Sure.
So that's why I kind of understand.
Okay, so we're looking at the function value. I'll do this one. P, the change is going down, it's negative, right? Q, it's 0, and for R, the tangent line is going to be positive. Positive numbers are bigger than negative numbers. 0 is bigger than negative. So
R.
that would be R,
This is Q.
right? And then that's the
And I had another thing for this. I put in the right answer, I think, and it's saying it's wrong. So I've got this graph, and it's one's from 0 to 8 period.
Mm-hmm.
8 is 1.45,
Okay.
and 1.45 minus 1.75 is negative 0.3.
Right. But it's in billions of dollars. I think that you need to multiply it by, yeah, multiply it by a billion.
Because it says right here $billion.
Okay, that should work. Let's make two single figures, the average rate of change of government funding for the first period is, so it's going down. But they since they want it to 2 decimal places, they don't want it as a fraction.
Okay. Alright,
Okay. Hi. Okay, send me an email. It just said 10.5, your name, I'll do it. But yeah, so otherwise
Okay, thank you.
I have two questions. The first one is, how did you make it ignore the first one on the table? What did you click to make it ignore the equal sign?
Good question. So I go over, so I use the arrows, I go over to the equal sign and I hit enter.
Enter,
Yeah.
and then it just ignores it.
And it ignores it. If I go back and hit enter, now it will graph it.
And then my second question, are the homeworks due tonight, right?
Yeah. So if you need more time,
I just need 24 hours because
Just
I've been
give
at
me-
work since like 7 a.m. So I'm
you
like
got
really
it. Yeah.
exhausted.
Just send me an email. I'm going back to my office right now. But yeah, I'll get them before midnight. I will get those extensions posted so that.
Okay, awesome. Thank you.
I'll get it to like Friday.
Okay. I appreciate it. I love how you teach, by the way.
Well, thank you.
Thank you, sir. Have a good one.
You too.
Hi, Professor.
Is it going good for you? A little bit better?
Yeah, go ahead. Yeah, I finished all the 10.4 and 10.5 at office hours, and I seem to get all this done, so that's good. The only thing is one of the first two homeworks, it was either 10.1 or 10.2. I didn't get to complete all the way through.
Send me an email. I'll do it. Yeah.
Okay, cool. Okay, cool. Thank you. I might. Do you have office hours on Thursday?
I do.
Okay, I might just come in then to
Perfect.
go over. Okay. Thank you.
Working better now? Is it making a little more sense?
Yeah, yeah, yeah.
Okay. Yeah, see, I do. Alright, let me check that off. It's there you go.
So I had a question on number 9 and then number 12 on 10.4.
Okay.
So I took the average rate of change and I got negative 0.16875, and I don't know if it wanted me to format it differently because
Yeah,
oh yeah,
so
yeah, hold on, this was
3 to 4.
this was what page is 12? Oh yeah, the 0. This was number 9 for some reason. This was 12.
Oh, okay.
Yeah. And then I put it as like everything I could try, and it's still
Two
marked it wrong.
significant figures. So I don't. If this is correct, what it's looking for is negative 1.69 because it only wants two significant. It doesn't want
Okay.
all of that. So that if it is correct, if it's from 0 to 8, got that, and then let's see. So at 8, it is halfway between those two, which is that 0.8? No, no. Couldn't find it for the arts. That should be. Oh shit! Why did I do it like this? This is 2.5 minus 1.35. It's a difference of 0.8, but it's only halfway between these two. So it's you kind of
So you add 0.8 or
you
wait no.
distances you had actually half of that, so you'd add 0.4, so it'd be 1.35 plus 0.4. So this should be 1.75,
I see.
and then at 0 to 2.15 is good, yeah.
Okay.
And so then it's gonna be actually no, this will be negative, but it'll be 5.4, right, I think. 75 plus 2.5, yeah, 8.4 over 8 should be negative 0.05.
0.05.
Yeah, and that's with two significant figures.
Okay. And then what is the significant figures in here?
They use that mostly in chemistry, but it just means that it's rounded to just two figures
After the decimal?
after the decimal.
Okay.
They call them significant because, again, we don't use them that much in math, but evidently it's significant because you wouldn't really go 3 decimals because it's only showing 2, so that's the accuracy,
Okay.
level of accuracy.
So if this was like 0.058, then it would be 6.
Right.
Okay.
Yeah.
and I don't need to change it because it's in the billions, so it would
Right.
be negative 0.0,
Negative
0.05.
Yes. Oh, should be number of significant figures. It's got two significant figures. Estimate to two significant figures.
Or is it negative 0.5?
Yeah. So subtract them. That's negative 0.4. 0.4 divided by 8. 8.5.
Yeah, I was so confused. I clicked on more information and it brought me to the book and it showed me this. And I thought this is like another language here.
Zero at the end of the answer. That's what it is.
I didn't know if I was supposed to use E or.
No. That would be. I mean, you could do it. Let's see. You could do 5.0 e to the negative 2, because that's showing, but. You've got two significant figures. Well, what question was that? Which section was that in?
12D 10.4. The 12 point. I mean the 10.4.
10.4. I can't remember if this one shows. I think it'll show me the answer when I look up that. Okay. 10.4, right?
Yes.
Okay. Let's see if I think. What's your last name?
Collins.
Okay, let's see. I think I can look up your exact. Tyler, right?
Yes.
Okay. 10.4. Oh, then I can look at your responses. You'll have credit for it either way, but it's just frustrating that I'd like to, because you've got enough for that.
Yeah, I'm so.
But-
confused.
Okay. See, yeah, the answer they give is negative 0.050. That's three. Oh, see, so the zero in the front doesn't count as a significant figure, so the 5 needs a 0 behind it. What? But it's a business class. We don't do like I said, significant figures is done over in chemistry.
Okay.
I don't know why they're doing. So that's what I mean. You've got the right answer.
Okay.
In fact, let's see if I can even just go. I think I can change. That's Oh. Override. Yeah, I get you almost there. Yeah, this doesn't let me go in and change that particular score, but I can add a bonus, so we put it on.
Thank you. And then number 9, I was confused about. I think we learned it today,
Yeah.
so I didn't know how to do it. But you take the derivative of 1 over x.
Actually not, because what they want the average rate of change.
Okay.
So you're gonna wanna plug in the 3, that'll give you your y answer, so that's 3, will give you 1/3, a y value 1/3, so that's 1.3 1/3. The second point is 4 1/4. And then you wanna do this same type of thing, so you got 3 and 4.
Yeah.
Okay, here, yeah, so 3 and 4. So we get the point 3 1/3. And that's y value, and then the other, so the coordinate, so x is 3, y is 1/3, x is 4, y is 1/4. So you can subtract those are your y values, just like you're doing here, and then the bottom you're gonna take 3 minus 4. No, cause we gotta get a common denominator.
Oh.
12, so you get 4 12s minus 3 12s, so 1 12. And the top,
I haven't done this in so long.
yeah, that's how you find
112.
yeah. And then in the denominator, you've got 3 minus 4, right, cause that's your x, like here you got your y's, that's gonna give you a -1, so it's 1/12 over -1, so it's -1/12. Does that make sense?
Yeah.
Okay.
I just didn't see those steps, and I was a little confused. Graph like this, or do we need a decimal?
If appropriate, specify the units of measure. Yeah, I think that's all. Yeah, you should, doesn't say significant figures, so.
Yeah.
Okay.
So. Yeah, I think that's right. Thank you.
You're welcome.